In the previous 2 days, we talked about homogeneous ODEs with constant coefficients. Today we're going to introduce a second variety of homogeneous ODE, which is called a Cauchy-Euler equation. Now, constant coefficient ODE had literal constants multiplied by all the different derivatives of y. For a Cauchy-Euler equation, the different derivatives of y are being multiplied by different powers of x. The different powers of x are always going to be an exact match to the derivative on the y. So the nth derivative of y is being multiplied by x to the nth power, plus potentially some constant number. The n minus 1 derivative of y is multiplied by x to the power n minus 1, plus potentially some constant. And all the way down the line until we get to the first derivative of y, which is multiplied by x to the first power and potentially some number. And the 0th derivative of y multiplied by no x's and potentially by some number. Now, in general, a Cauchy-Euler equation can have a function of x on the far right side. We will be dealing with that case a couple of days from now. But today we will be dealing with the specific case that the right-hand side of the equation is equal to 0, making this a homogeneous ODE. Now, the technique for solving a homogeneous Cauchy-Euler equation is very similar in spirit to what we did for homogeneous ODEs with constant coefficients. The idea is to make an educated guess about the format of a solution. For constant coefficients, we guessed that the solution had an exponential format. For Cauchy-Euler, we guessed that the solution has the format of a power function x to the power m. Make this guess, plug the guess into the ODE, simplify the resulting equation, and then solve for m. And just as in the previous section, we have language for the equation that we get after we plug in our guess and simplify. In this section as well, that equation is also called the auxiliary equation. Now we're going to go ahead and break it down into 3 main cases, the same 3 cases that we considered yesterday and the day before. When the auxiliary equation has distinct real roots, when it has complex roots, and finally when it has repeated roots. Let's deal with the easiest case first, when the auxiliary equation has distinct real roots. Let's solve the ODE. Y double prime multiplied by x squared, y single prime multiplied by a single x and the constant -2, y with no derivatives multiplied by no x's with the constant -4, and 0 on the far right side. So this is truly the format of a homogeneous Cauchy-Euler equation. Which means that it's appropriate for us to guess a solution of the form y equals x to the power m. Now let's figure out what consequences that guess would have. If I took the first derivative of this guess, then by power rule, I would be looking at m times x to the power m minus 1. And if I took the second derivative, then m minus 1 would come down, and the power would be decreased further to m minus 2. So let's stick this information back into our differential equation. And we get x squared times m minus 1, x to the m minus 2. We get -2x times y prime, which is m x to the m minus 1. And we get minus 4 times x to the power m. That needs to equal 0. Notice that when we have x squared multiplied by x to the m minus 2, these two can be combined into x to the power m. The same thing is true with this 1x and this x to the m minus 1. So all three terms contain an x to the power m. So what we're going to do is we are going to divide out that x to the m. Now there's one small technical problem that we can encounter when we divide out x to the m. Unlike the exponential function from the previous two sections, x to the m can actually be equal to 0. And we want to make sure that we are not dividing by 0. So whenever we actually solve a differential equation using this method, we always assume that x is strictly positive. Strictly positive to make sure that we're never actually dividing by 0 when we divide out x to the m. Now once we do this, we get m times m minus 1 minus 2m minus 4 equals 0. In other words, m squared minus m minus 2m minus 4 equals 0. In other words, m squared minus 3m minus 4 equals 0. Now, factoring that, we get m minus 4, m plus 1, which leads us to m, which leads us to m equals 4, m equals negative 1. And from these two values of m, we get two linearly independent solutions, x to the power 4 and x to the power minus 1. Once again, you can confirm, using the Wronskian, for example, that different m's give linearly independent solutions. So now we have our general solution that y is equal to c1 x to the 4th power plus c2 x to the negative 1, which is valid for positive x's. Case number 2, what happens if your auxiliary equation has a repeated root? So in that case, if your root is repeated and has multiplicity 2 specifically, if it shows up 2 times when you solve your auxiliary equation, then your two solutions can be found by taking x to the power m as one solution, and then to construct your second linearly independent solution, you can just take your x to the power m and multiply it by the natural log of x. You could figure out this result using reduction of order the same way that we did yesterday. I'm just going to skip that part. You already know the basic idea of that derivation, and I'm just going to give you the conclusion of that. If your m is repeated twice, the second solution can be found by just multiplying by natural log. So for example, let's solve the ODE, where we have 4x squared y double prime plus 8xy prime plus y is equal to 0. So if I set up my guess, y equals x to the power m, so that y prime brings down an m, and y double prime brings down an m minus 1, then when I plug that into the ODE, I get 4 times m minus 1, x to the m, plus 8 times m, x to the m, plus x to the m equals 0 after simplification. Once again, we're going to divide out x to the power m, which gives us 4 times m minus 1, plus 8m plus 1 is equal to 0. So that's 4m squared minus 4m plus 8m plus 1 equals 0. 4m squared plus 4m plus 1 is equal to 0. Now when I factor this, I get 2m plus 1 plus 2m plus 1 times 2m plus 1. Which means that m equals negative 1/2 is a repeated root with multiplicity too, because it appears twice in our auxiliary equation. Therefore, by the rule above, our two linearly independent solutions would be y1 equals x to the power negative 1/2 and y2 equals x to the power negative 1/2 multiplied by a natural log. Therefore, our general solution would be our first solution times C1 plus our second solution times C2. Very, very similar to what we saw yesterday. Yesterday, when we had a repeated root, we took our exponential and multiplied it by an x. Here, where we have a repeated root, we take our power function and multiply it by a natural log. The final case is, what if you solve your auxiliary equation and you find that your auxiliary equation has complex roots? Roots of the form alpha plus minus beta times I. In this case, once again, I'm going to skip the derivation and just give you the formula. In this case, your two linearly independent real-valued solutions are going to be given by x to the power alpha, x to the power real part, cosine of beta, but not beta times x this time, beta times natural log of x. y2, you may be able to anticipate what's coming. Same thing, except with a sign. Once again, very similar to what we did yesterday. Yesterday we had an exponential in front, multiplied a cosine of beta times x, or sine of beta times x. And this time we have a power function out in front, multiplied by either cos or sine of beta times natural log of x instead of just regular x. For example here, let's consider the ODE where we have x squared y double prime plus 16y is equal to 0. Once again, we're looking at a Cauchy-Euler equation, x squared multiplied by y double prime. So we're going to guess that the equation has solution of the form x to the power m. So that y prime brings down 1m, and y double prime brings down an m and an m minus 1. So if I stick that data into our differential equation and simplify a little bit, I get that m times m minus 1 x to the m plus 16x to the m is equal to 0. And after canceling out those x to the m's and simplifying a little bit, I'm left with the equation m squared minus m plus 16 is equal to 0. Now, to my knowledge, this can't be solved by factoring, so you know what I'm going to use.
So minus the square root of b squared minus
b plus minus the square root of b squared minus 4ac all over 2a, which looks like 1/2 plus minus, what is that? Negative 63 under the square root. So root 63 times I over 2. So 1/2, the real part, would be our value of alpha. And the imaginary part, the part multiplied by I, would be our value of beta. So our two real valued independent solutions would be x to the power 1/2. Cosine of root 63 over 2 times natural log of x. y2 would be the same thing except with sine instead of cos. And then finally, as always, our general solution is just a combination of these two. That concludes today's material. We introduced a new type of homogeneous ordinary differential equation, which was called a Cauchy-Euler equation. The big difference between a Cauchy-Euler equation and an equation with constant coefficients is that a Cauchy-Euler equation had powers of x next to the different derivatives of y. The technique for solving a Cauchy-Euler equation was super similar to our technique for solving ODEs with constant coefficients. It's just that the guess had a different format. For constant coefficients, we guessed an exponential function e to the rx, and for a Cauchy-Euler equation, we guess a power function x to the power m.